Good morning, everyone. I am Swapnil Lakshman from the Department of Microbiology, and today I am going to talk about the topic bioleaching. So, before moving on to bioleaching, let us talk about biohydrometallurgy, since bioleaching is one of the applications of biohydrometallurgy. So, if we divide the word into its literal meaning, it comes down to bio, which means related to living organisms, hydro, which relates to maximum processes taking place in the aqueous environments, and metallurgy, which deals with metal production and treatment from its solution and ores. So overall, biohydrometallurgy is the method for obtaining metals from their ores by using microorganisms. So as you can see from this image, there are various applications of biohydrometallurgy like microbial mining, oil recovery, bioleaching, water treatment, and many other applications. Post-industrialization, there has been an extensive use of metals for various purposes that have led to metal contamination of soil environments and nearby water bodies by eutrophication and biomagnification. So, the assessment of its risk to terrestrial environments as well as human and other plant and animal health is very essential, right? Bioleaching or biooxidation employs the use of naturally occurring bacteria harmless to both humans and the environment to extract metals from their ores. Bioleaching is not only essential for degrading the metals that are contaminating the soil, but this method can also be used to recover certain metals from their sulfide ores by the conversion of insoluble metal sulfides into water-soluble sulfates. Bioleaching is used to recover metals like copper, zinc, lead, arsenic, antimony, uranium, nickel, molybdenum, gold, silver, and cobalt, and is widely used in countries like Australia, Canada, Chile, China, Indonesia, and United States. So these are some of the examples of microorganisms that are involved in bioleaching. Under bacteria, there can be Acidobacillus pyroxidans, Acidobacillus thioxidans. Under fungi, there can be Aspergillus niger, Penicillium simplicissium. There are certain other microorganisms that can leach the metals from their ores. But these are the microorganisms that are most extensively studied and used in various industries for extracting metals from their respective ores. Thiobacillus pyroxidans and Thiobacillus thioxidans are two of the most common types of bacteria that can leach the metals from their ores. Here I have listed some of the features of these organisms. So Thiobacillus pyroxidans is rod-shaped, it is gram-negative, strictly aerobic. Under aerobic condition, it uses ferrous ion as an electron acceptor and can actually oxidize the ferrous ion to ferric ion. Under anoxygenic condition, it uses that ferric ion as an electron acceptor. They are moderately thermophilic with temperatures ranging from 20 to 35 degrees Celsius and pH of about 2. Thiobacillus thioxidans is very similar to Thiobacillus pyroxidans, but they can't oxidize the ferric ion. As I have already mentioned, that most of this leaching is done on sulfide ores. So this bacteria can oxidize the ferrous ion and sulfur to produce ferric ion and sulfate. This ferric ion in turn reacts with the sulfide minerals to produce ferrous ions and sulfate. So you can see that there is a continuous cycling of ferrous ions and ferric ions during this whole bioleaching process. Now we will see the materials and substrates that are required for bioleaching. We would obviously require the metal ores from which metals need to be extracted that will act as the source of energy for these microbes. Proper supply of oxygen is required if the microbes are aerobic, and if it's anaerobic, then the fermenter needs to be completely airtight. Suitable media, carbon dioxide, nitrogen dioxide needs to be provided for the optimum growth of microbes. Optimum pH of 2.3 to 2.5 since these are acidophilic that needs to be maintained. Inoculation using suitable strains of bacteria needs to be done along with the maintenance of mesophilic conditions of 30 to 50 degrees Celsius. Suitable types of fermenter that will have a proper steering mechanism for optimum distribution of media, nutrients and oxygen throughout the fermenter is necessary. Along with this, sprinklers and proper airflow is also essential. Catalysts can also be added to increase the rate of reaction. So what exactly happens in the bioleaching process? The oxidation of the substrate starts from the cell membrane itself. The main reaction here is the oxidation of sulfide by ferric ion. The electrons will pass into the cell and are used in biochemical processes to produce energy for the bacteria while reducing oxygen to water. The main role of the bacteria here is the regeneration of the ferric ions that will keep the reaction proceeding in the forward direction. So there are quite a few types of bioleaching which I've listed here. For example, in situ bioleaching, heap bioleaching, vat bioleaching, tank bioleaching, and autoclave bioleaching. I'll not go into the details of these types since the underlying principle is same for all these types of bioleaching. So the metal that has been leached now needs to be recovered for further use, right? So for that reason, it can be recovered by various methods like solvent extraction or liquid-liquid extraction, which is a method to separate compounds based on the relative solubilities into separate immiscible liquids. Then there is biosorption, which is a physiochemical process that involves the binding of metal ions to a surface adsorbent. So it is a passive method to remove metal ions that does not require any inputs of energy from the aqueous effluents. Thirdly, there is bioprecipitation, which is a kind of a bioremediation strategy that involves like converting the concentration of free metals to insoluble complex, thereby reducing their concentration from the Bioleach solution. So we are basically converting the metal ions, like the free metal ions that are present, into insoluble complexes so that they can be extracted from their respective Bioleach solutions. And lastly, there is electrowinning or electroextraction that uses electric current for the deposition of metals from their ores that are found in the Bioleach solution. So this image basically summarizes the whole process of bioleaching. You can see that the metal ore, preferably a sulfide ore, is being used from which the metal is to be leached. Prime advantage of bioleaching as compared to other conventional forms of leaching is that it can use low grade ores, like the ores that have low concentration of metals, and from there we can basically leach out the metals. Then these ores are crushed in these ball mills or rod mills, and then they are sent to a suitable bioreactor where the optimized microbes are being added. Optimum condition is being provided for their maximal growth and maximized bioleaching. The leachate that is obtained contains the dissolved minerals. They are collected and sent for recovery and purification, and in this way we can extract metals from their ores. So coming to the reactions that are involved in bioleaching, in the first reaction, you can see that the metal sulfide is getting oxidized to thiosulfate by ferric ions that in turn is getting reduced to give ferrous ion. The ferrous ion in the next step is getting oxidized back to ferric ion. This is done by the bacteria. Lastly, the thiosulfate is also oxidized by this bacteria to give sulfate. The ligand metal complex is extracted from the solution using an organic solvent, and the metal can be concentrated and separated and purified by displacing the metals with iron from scrap iron. So since bioleaching involves the use of live microorganisms, so like all other processes, there would be certain factors that influence it, right? For example, under physiological factors, you can see there is temperature, pH, light, pressure, etc. Microbial diversity and whether the microbes are in log phase or in lag phase will also determine the rate of bioleaching. The properties of minerals, like if it is a high grade ore, low grade ore, the grain size, porosity will all influence the process of bioleaching. Finally, the processing, purification methods, the handling procedures will influence the process as well. So here I've listed some of the advantages of bioleaching. It is simpler, cheaper as compared to other conventional leaching processes. The process is environmental friendly. and there is very little use of chemicals, and the whole process is run by microbes. Bioleaching can reduce the amount of greenhouse gases, and the most important one is that very low grade ores can be used for the extraction in this process. So just like advantages, there are some disadvantages of bioleaching as well. For example, the whole bacterial bioleaching process is very slow. Sometimes heat is required to dissolve the ores in water that can kill the microorganisms. These microorganisms can produce toxic chemicals that need to be removed from time to time so that the metals don't get degraded. Lastly, since this is generally carried out in batch fermentation, so we know that if a batch fermentation is started once, the process cannot be stopped easily or immediately. Now we will have a look into the bioleaching processes for some metals, starting off with gold. The ores from which gold is to be extracted are calcite, slavinite, and bauxite. Unlike other metals, in the case of gold, we cannot extract from low-grade sulfide ores. Gold ores need to be pre-treated by roasting prior to cyanide leaching, which is once again an expensive process. Sodium cyanide leaching process converts gold to a soluble cyanide complex, and this is done mainly by thiobacillus peroxidans. You can see the reaction that occurs during gold leaching in this picture. Now, coming to bioleaching of uranium, the ores from which uranium can be extracted is uraninite or pitch blende, branerite. Uranium ores are generally very low-grade ores and is insoluble and can be converted to a soluble form by oxidation with ferric ions. This is the reaction that you can see in the left-hand side. Acidobacillus peroxidans deoxidizes this ferrous ion to ferric ion. This ferrous ion is oxidized to ferric by chemical oxidants like fluoride, manganese dioxide, and hydrogen peroxide. So both this can be done by chemical reagents like these, or we can use bacteria like Acidobacillus peroxidans as well. This ion, like this ferric ion, is in turn acting as an oxidant to convert the uranium dioxide chemically to the leachable form, that is uranyl sulfate. The last metal that we will talk about is of copper bioleaching. Copper is leached from ores like chalcopyrite, chalcocite, and cobalite. All of these are often low-grade ores. Acidothiobacillus plays a major role in this copper bioleaching. And on the left-hand side, you can see the reactions that are happening during this bioleaching of copper. So the bioleaching process is now being used in various other sectors for the welfare of mankind. We would be discussing a few of them here. For example, like microbes are now being used to tackle mine waste, which is in the form of corrosive acid that is left over as a result of mining. The discovery of certain microbes from America, Wales, and the Caribbean island that can survive in these extreme environments can be used to address serious environmental hazards at abandoned mines and soil heaps. So coming to the second application is bioremediation. It is the process of using microbes to decontaminate affected areas by removing the pollutants, contaminants, toxins from the soil, water, and other environments. Bioremediation of metal contaminated soil can be done by soil flushing, soil washing, phytostabilization, and phytoremediation. So in conclusion, bioleaching is an eco-friendly and cost-effective process of biomining. It is scalable, versatile, and can be used for low-grade ores from which extracting metals from other conventional methods is very difficult. Biomining can be a key solution for metal recovery in the coming years due to the growing demand in industries like electronics and renewable energy. The challenges that we need to overcome is that the process requires optimization for faster rates and for a broader optimization. These are my references. And finally, thank you everyone for listening and have a nice day.